In this video, we're going to work through the 8 questions in exercise 13.2. The formulas we're going to need are all listed out here. So F is equal to minus Ks, that is Hooke's law. A is equal to minus omega squared s, that's the formula for acceleration in simple harmonic motion. T, the period, is equal to 1 over F, which is a frequency. Frequency is equal to 1 over T, which is a period. Finally, T is equal to 2 pi over omega. That's the last formula we need. This one we'll look at in the next section. It's another way to calculate the period, but it's based on pendulums and we won't use it in this section. So the first question says, a particle executing simple harmonic motion makes 20 full oscillations in 4 seconds. Find first off the period and second off the frequency. So again, going back to our definitions and our understanding of what oscillations is, an oscillation is over and back, so it goes over and back 20 times in 4 seconds. So by definition, the period t is the time taken for one oscillation. So 20 oscillations takes 4 seconds. So divide both sides by 20, which tells us one oscillation is 4 over 20 seconds. So when we do that calculation, the time taken for one oscillation is 0.2 seconds. So that's my period, 0.2 seconds. Then I'm asked to find the frequency of motion, so I use the simple formula F is equal to 1 over t, where t is the period. 1 over 0.2 seconds is equal to 5 per second, and per second are also known as hertz. So my frequency is 5 hertz, which again makes sense. I would get 5 waves in 1 second because it takes a fifth of a second for one oscillation. So question 2, a pendulum in a school lab executing simple harmonic motion makes 50 oscillations in 20 seconds. So again, they give us this background just to know that it's simple harmonic motion so that we can use our formulas. So what is the period of the pendulum? Similar to above, so kind of applying this formula here, if I want to know what the period is, it's the time over the number of oscillations. So here I've formalized it a bit. So the period is the time taken in seconds over the number of oscillations. The time taken was 20 seconds. That's over 50 because it was 50 oscillations. So it's 20 divided by 50, which gives me 0.4, and second is my unit, which is the unit for time. So that is question 2, nice and simple. On to question 3. Tells us the acceleration of a particle executing simple harmonic motion is 2 meters per second squared when it is 50 centimeters from the equilibrium position. What is its acceleration when it is 10 centimeters from the equilibrium position? And finally, what is its displacement when its acceleration is 0.5 meters per second squared? This is a typical feature of the simple harmonic motion questions. You have a few different cases, a few different areas that they look at. So they first off tell us that when it's executing simple harmonic motion, when it has an acceleration of 2 meters per second squared and is 50 centimeters from the equilibrium position. So that's one set of information. So we'll take that as itself and we'll move on. Then the acceleration is going to be changed because again, acceleration is variable, maximum at the end, directed towards the middle, and it's always changing when it changes position. So in the second case, we want to know the acceleration when it's 10 centimeters from the equilibrium position. And finally, they want to know where it is when the acceleration is 0.5 meters per second. So again, just focusing on the first line because that's our first case. Our acceleration is 2 meters per second. Our distance from the equilibrium position is 50 centimeters, which is 0.5 of a meter. I'm going to, in this case, I have A and S, so that's going to be the simple harmonic motion formula that I'll use to find omega. So I'll get what omega is from this equation. The sign is only about direction, so it doesn't make any difference for the numbers. We want to know the numbers and we can infer the direction then afterwards. So omega squared, if I divide both sides by S, is equal to A over S. Then to find omega, I'll get the square root of both sides. Once I do that algebra, I've got my acceleration 2 meters per second over my displacement of 0.5 meters. So that gives me the square root of 4. So my omega here, the square root of 4, that is 2 per second. So that's my units, that's my calculation. Here I found what omega was, but typically it might be simpler and more useful to just get omega squared instead. So I could just work from this formula here. So to find the omega squared, I would have 2 over 0.5, which again will give me 2 squared. So that's a fine thing to do. It just depends on what you need. Some formulas you need omega squared, so we're going to need omega squared again. So I could have just found omega squared, but sometimes you do need omega and then you need omega squared and vice versa. So I can sometimes, when I know what I'm doing, just get omega squared. You could always get the square root of the answer then at the end. So again, this is their second case. So now we don't know the acceleration, but we know the displacement is 10 centimeters from the equilibrium position. So that goes to 0.10 meters. And my formula A is equal to minus omega squared s. I found that omega was 2, so I substitute that in. I know my displacement is 0.1, so I sub that in. So my acceleration is minus 0.4 meters per second squared. So what that means is the acceleration is 0.4 meters per second, and it's in the opposite direction to the displacement. So if the displacement is this way, acceleration is the other way. If the displacement is up, acceleration is down, and so on. Then in the third case, I'm asked to find the displacement when we have an acceleration of 0.5 meters per second squared. So again, I know what my omega squared is. I found that here. That is 4 per second squared. I know my acceleration. I want my displacement. So I take my basic simple harmonic motion formula. I divide both sides by minus omega squared. Again, you can drop the minus. It doesn't really matter. And then I substitute this in. So I'm told my acceleration is 0.5 meters per second. So this shouldn't be a minus here. I should have just took the 0.5. It's in the opposite direction of the displacement, so that would be kind of the minus effect, but you can just drop the minus if you like. So that's my acceleration. On the bottom line, I have my omega squared, which is a constant, so that's going to be the same all the way through. Omega was 2 per second, so omega squared is 4 per second squared. So then I get the answer that my displacement is 0.125 meters. So at 0.125 meters, 12.5 centimeters, I will have an acceleration of 0.5 meters per second squared. Then we're on to question 4, which I think is the most difficult one out of the 8. So it tells us the maximum force acting on a particle which moves with simple harmonic motion is 60 Newton. The mass of the particle is 12 kilograms. If the acceleration of the particle is 1 meters per second squared, when its displacement from the equilibrium position is 10 centimeters, find the amplitude of the motion. So again, there's a lot going on here, and when there's a lot going on, it's good to do diagrams. So they tell me the maximum force acting on the particle. That's going to happen at the top when the spring is all the way scrunched up, so maximum compression. That's going to react, push down with a restoring force of 60 newtons. The mass itself is 12 kilograms, so I've taken that information over here. So the maximum restoring force is 60 newtons. So I have this mass and I have this force when it's at the top. It could be at the bottom when it's at its maximum extension. It's about to spring back, but I just went for this one, just kind of 50-50. A bit easier to draw, a bit more compact. Then I know at some other time the acceleration is 1 meter per second when it is 0.1 meters away from the equilibrium position. So the mass is still 12 kilograms, but when it's 0.1 away, my acceleration is 1 meter per second. So again, in this second case, the first case is A, it's all the way compressed. The second case is B, it's moving closer to the central position. So my acceleration here is 1 meters per second, the mass is 12 kilograms, and my displacement is 0.10 meters. And then I've shown my equilibrium position with the red. Now again, these are all assumptions. It could be below it, but it doesn't really matter. We can just go with any case. So again, logically, I got to figure out what I need to do. So we need to find the displacement from the equilibrium position when the particle is at the top and the bottom, because that's what the amplitude is. So amplitude is its distance from its rest position. So I want to see where it is from the rest position up to here when it's at the max. That's what I need to find. At this or these positions, so at the top or the bottom, because it'll be the same, the force and the acceleration are at a max. We're told the maximum force, the maximum restoring force is here, and we also know that the maximum acceleration is when it's at the top or the bottom. So I know the force and I would like to find the acceleration. So that gives me my clue that I need to use F is equal to ma. I'm given the mass, I'm given the force, so if you ever have F and m, finding A is the good next step. So if F equals ma, A is equal to F over m divided across, then I substitute in my force is 60 newtons, the mass is 12 kilograms, so at the top and the bottom, the maximum acceleration is 5 meters per second squared. So again, I've built up, I've found something, I'm on the right path. What I need to find is the displacement at this position. But as A is equal to minus omega squared s, I've just found my acceleration, that's good, but I don't know omega and I need to find s, so that's two unknowns. So I need to get what omega squared is first. So I'm going to use this omega squared, so I need to find out what that is first. So looking at this second, when I look at this scenario, I know my acceleration and I know my displacement, so I can find then omega squared. So A is equal to minus omega squared s, that's our SHM formula. Divide both sides by s, forget about the equals, forget about the minus. So omega squared is 1 meter per second, because that's what I'm told, when it's at a displacement of 0.1 meters. So omega squared, the constant, and that is a constant regardless of position, is 10 per second squared. So now I know what that is, so I use this formula to find out the displacement when it's at the max acceleration. So I've found out from up here that the acceleration at the top is 5 meters per second. My omega squared, my constant, is 10, so I get a displacement of 0.5 meters. So the maximum displacement is 0.5 meters, and that will be 0.5 meters away when it's either at the very top or at the very bottom. I think that's as hard as it gets, so hopefully we'll be able to do all of these ones. So a mass of 4 kilograms moves a simple harmonic motion of period 0.5 seconds. Find the force acting on the mass when it's 4 centimeters away from the equilibrium position. So here there's this change. Now we're beginning to find these periods. So we have it at the top, and then it's going to move down to the bottom. So what the period is the time taken to go from the top to the bottom and back to the top. So we have time is equal to 0.5 seconds. We're told that that's one oscillation. We're also told that the mass is 4 kilograms. We have we want to know the force acting on the mass when it's 4 centimeters. So 4 centimeters is 0.04 meters. So we find the force. So that's my information. That's what I have. So I got to use all of this information to find the force. So because I'm finding force, I'd need to use either Hooke's law, F equals minus Ks, or Newton's law, F equals ma. In this question, I have no way to find the spring constant K, so I'm going to have to use F is equal to ma. So we need to find the acceleration. If we find the acceleration, we know the mass, we can get the force by this way. And it's easier to find the acceleration than the spring constant. So we need to find the acceleration, so we're looking for A. We don't know omega squared, and we do know S because we're given mass. So first we get omega. So as we were given the period, t is equal to 0.5 seconds. We're told that in the question. Then we can use this other formula. T is equal to 2 pi over omega. So we can use this other formula to feed in the value we need there. So when we do the algebra, we multiply both sides by omega and then we divide by t. So we get omega is 2 pi over t. That's my formula for omega. 2 pi is a constant. T, I'm told, is 0.5 seconds. So I get that omega is equal to this. And again, that's just omega, not omega squared. Then I go back to this formula to find my acceleration. It's minus from the formula. This constant for omega in there squared multiplied by the displacement, which is 0.04 meters. That tells me my acceleration at this point is 6.316 meters per second. Then I can find my force. So my force, the mass, is 4 kilograms by the acceleration, which is this, and that gives me my force, just what I was asked for. On now to question 6. It tells us again, a particle executes SHM. What is the period if the acceleration is 3 meters per second when its displacement from the equilibrium position is 0.5 meters? So again, what is the period? Acceleration is 3 meters per second squared when it is a distance of 0.5 meters from the equilibrium. I know my period. This is the one I'd like to use. T is equal to 2 pi over omega. However, I don't know what omega is, so I can use this other formula. From here, the acceleration from simple harmonic motion formula, A is equal to minus omega squared s. So when I do my algebra, omega, because I need omega, not omega squared, because omega's got to go in here, I get the square root of A over s. So that's omega. So I combine the two formulas here, so I replace omega with this. So I get 2 pi over the root of A over s. I know A is 3 and s is 0.5. So I substitute it in and just do the whole thing together, and I get my period is 2.565 seconds. Question 6. Question 7. When the displacement of a particle executing SHM is 14 centimeters, its acceleration is 2.5 meters per second squared. What is the frequency of the motion? So again, take my information. I got my displacement, I got my acceleration, and ask for frequency. I know from my theory my frequency is 1 over the period. So I need to find the period. If I can get my frequency, if I know the period. The period, just from the formula above, is 2 pi over the square root of A over s. So 2 pi over omega. Omega is the square root of A over s. So I can substitute in my figures. I have an A, I have an S, so I substitute in those and I get my period. So I know what the period is. It's 1.487 seconds. That will then give me the information I need to use this. So F is equal to 1 over T. I substitute that figure in. So my frequency is 0.673 per second, and a per second is a hertz. Finally, question 8 tells us the period of a particle executing simple harmonic motion is 1.5 seconds. What is its acceleration when its displacement from the mean position is 25 centimeters? Again, they'll use lots of these different terms: mean position, equilibrium position, maybe the center of gravity, the natural position, whatever they use. Don't get too caught up. It's just the mean position, the average position, the middle, so to speak. So I'm told the period is 1.5 seconds. I'm asked for the acceleration and I'm given my displacement. So I'm only given those three terms. So I have A and S, so that will allow me to find omega squared or omega. So A is equal to minus omega squared S. I would like to find omega because I'm looking for, if I need to use this formula because I'm looking for acceleration, so I'll need to use the period to get what omega is. So my formula is before the period is equal to 2 pi over omega, cross multiply and divide, we get omega is 2 pi over T. I'm told that T is 1.5, so I found what omega is. Omega is 4.187 per second. Then I can now use my simple harmonic motion formula to find the acceleration, which is what I want. So the acceleration is minus omega squared S, and then that gives me my figure of A is equal to minus 4.39 meters per second squared. And again, just to drive the point home, the acceleration is 4.39 meters per second, and it's in the opposite direction to the displacement. So whichever way it's moved, the acceleration is going to be in the opposite direction. So there are the exercise questions. I hope you can understand them, and best of luck solving them out.